will continue with our discussion on displacement analysis of constrained mechanisms. So, in this lecture we will look at the example of the inverse kinematics of a 4R chain. So, this is one of the problems of displacement analysis. So, just to review what we have already discussed. So, we want to find out the input output relation, which is the subject matter of displacement analysis. So, we had looked at these examples where we would like to know, given an input, what will be the output, or inversely given an output or for a specified output or a required output, what should be the input. In the case of robots, we have seen that successive displacements generate a path, and the path of the output link or the end effector is what we seek to find out. So, here also you have these two problems, given the actuator throw or actuator displacement, what is the output, or if I need a certain output, if I need to place the bin or the end effector of this robot at some point, what should be the angles theta 1, theta 2, theta 3 in the case of this Puma robot manipulator. So, we have discussed these two problems, the forward kinematics problem, which is stated as, given the actuator inputs, find the output displacement, or the inverse kinematics problem, for a specified output displacement, find the actuator inputs. So, for example, in this chair, if I want to go to the standing position, what should be the throw of the actuator, or in this bin, if I want to position the bin, what should be the extensions of the hydraulic actuators. And as planned, we are proceeding with constraint mechanisms. We had looked at the forward kinematics of 4R chain. Now, we are going to look at the inverse kinematics of a 4R chain. So, what is the inverse kinematics problem for a 4R chain? Here I have stated that. So, if I am given theta 4, I am given theta 4, I have to find theta 2. That is the inverse kinematics problem. So, given the output, what should be the input? Okay. So, here let me again draw the coordinate system. So, theta 2 is this angle, and theta 4 is this angle. And this angle with the horizontal is theta 3. So, once again I can express coordinates of point P. So, this is x p, and this is the y coordinate of P. L 2 cos theta 2 is x p and L 2 sin theta 2 is y p. Similarly, I have for point Q L 1 plus the contribution of this vector in the x direction is L 4 cos theta 4. So, L 1 plus L 4 cos theta 4 is x q, and L 4 sin theta 4 you can check is y q. So, therefore, again L 3 can be expressed as, so square of P q, which is L 3 square, is nothing but x cube minus x p whole square plus y cube minus y p whole square. So, if I substitute these expressions, I will get this. Now, if you open this up, then we have seen we have various terms. We can now, because we now want to find out theta 2, I will look at coefficients of sin theta 2 and cos theta 2. And club all the other terms which are independent of theta 2 on one side. So, I will call this as A, this as B, and this as C, and we have looked at, if you open this up, then you can do this manipulation and finally come to this form which we have seen in the previous lecture. So, formally let us see what A, B, C are. So, here I have written out for you. So, A sin theta 2 plus B cos theta 2 is equal to C. Here A, B, C are now functions of theta 4 which is specified. So, A is sin theta 4 and B and C have these expressions. We are to solve this equation because theta 4 is given. So, A, B, C are all known. I have to solve this equation to obtain theta 2. Once I have theta 2, I can also find out theta 3. This is theta 3 with the horizontal. So, tangent of theta 3 is y cube minus y p by x cube minus x p, that we have seen also previously. So, if you substitute those expressions, you will get this expression that I have written out for you. So, right now our objective is to solve this equation. Once again, we will do it the way we have done before. Every time I will mention that we are doing this because this will have two solutions. There will be two solutions of theta 2. We will later look at it graphically also. There are two solutions of theta 2 and we would like to find out these two solutions of theta 2, both the solutions, because when we do it on a computer, it has to be told how to solve so that it gets both the solutions. If you just do sine inverse or cosine inverse, it gives one solution. So, we go over to tan of half angle. So, tan theta by 2, and that is what we are going to look at. So, solution of A sin theta 2 plus B cos theta 2 equal to C. We have looked at this derivation before, but let us go through it again just to make it clear and you get used to this. So, I substitute here x as tan theta 2 by 2, and I can then express the sin theta 2 and cosine theta 2 in terms of tangent of theta 2 by 2, and we have looked at these derivations. And substituting these forms in the first equation, we get this quadratic equation. We have to solve for the roots of this quadratic equation, and we all know how to express the roots of this quadratic equation in terms of the coefficients. So, let us look at that again. So, this is our quadratic equation. The solutions are given here, and the solution is actually tan theta 2 by 2, and these A, B and C have already been expressed before. So, let us look at the solution formally. So, tan theta 2 by 2 is given by this expression in terms of A, B and C, where A, B and C are completely known because theta 4 is specified. So, we have to find out theta 2, and this is done by taking the tangent inverse. Once I have theta 2, I can solve for theta 3. If I have this, I get two solutions of theta 2, theta 2 1 and theta 2 2 by taking these two signs, one the negative sign and then the positive sign. I have these two solutions. Corresponding to these two solutions, I can solve for solutions of theta 3. So, as you know, this will also have two solutions. So, every time we do this tangent inverse, we must use this A tan 2 y comma x function for the correct quadrant. So, what is y? So, y is the numerator every time, the y is the numerator. This is x, here also this is y, this is x, this is y, this is x. In some implementations, this is reversed. So, arc tan 2 x comma or arc tan x comma y. So, you have to figure that out in that software or in that programming languages, but mostly it is A tan 2 the numerator comma the denominator. So, this comes from this idea. So, this is x, this is y, this is y x, and this is the angle. So, tangent of theta is y divided by x. So, that it finds out by looking at the sign of y and x, that is why it requires separate entries of the numerator and the denominator. Okay. So, let us proceed further and look at this solution graphically. Now, this gives us a clear picture or visualization of the solutions. Why do we have two solutions, for example? We can ask the question. So, this graphical interpretation gives us that. So, in this problem, as you remember, we were given theta 4. So, theta 4 was given, and we were supposed to find out theta 2. That was the inverse kinematics problem. So, since theta 4 is given, so this hinge at the end of L4 is fixed. So, what can change? L3 and L2, how they are connected. So, this is one way, this is one solution. As you can see, L2 can rotate along this circle, and L3 can rotate on this circle. So, the hinge can rotate on this circle. Now, both the hinges must be at the same point. So, it is the intersection of the two circles that are the possible ways we can assemble. So, there are two solutions, one is this black, the other, let me try to draw that. So, this is the second configuration, second solution. So, correspondingly so given theta 4, you have two solutions of theta 2, one is this solution, the other is this solution, and you can have therefore two solutions of theta 3, this solution or this solution. So, we have two solutions, and these are the two assembly modes. Now, whether they are distinct or same, that will depend on whether this mechanism is a Grashof mechanism or a non-Grashof mechanism. So, that is the visualization of the solution. So, every time please remember that when you take this tangent inverse, please use the a tan 2 function, a tan 2 y comma x, to get the correct quadrant. So, this makes it amenable for computer programming. So, let me summarize what we have discussed today. We have continued with the displacement analysis problem, and in today's lecture we have looked at the inverse kinematics of a 4R kinematic chain. So, with that I will close this lecture.